In the beginning, there was a question, whispered not by scientists with their instruments of glass and steel, but by the human heart gazing upward into the velvet darkness. A question etched into the earliest myths, carried on the smoke of campfires, and woven into the very fabric of our longing. Are we alone? Is this world, with all its beauty and terror, its fleeting joys and profound sorrows, the only one? Or does the cosmos, in its infinite silence, hold other realms, other stories, other versions of ourselves? For millennia, this was the province of dreamers and poets, of shamans and philosophers. It was a question of the spirit, answered not with data, but with imagination. Ancient Hindu sages spoke of endless cycles of creation and destruction, of universes breathed into existence by Brahma, only to be absorbed back into the divine sleep, a cosmic rhythm stretching across eons they called kalpas. They envisioned a reality of layered realms, countless lokas, from the earthly to the celestial, each with its own laws and beings, a hierarchy of existence that stretched the mind beyond a single creation. In the bustling agora of ancient Greece, amidst the debates of democracy and the search for first principles, the philosopher Democritus of Abdera turned his mind not to politics or ethics, but to the nature of things themselves. With a staggering leap of intuition, he proposed that all of reality was composed of tiny, indivisible particles he called atomos, meaning uncuttable. And from this radical materialism, another, even more radical idea emerged. If there are an infinite number of atoms moving in an infinite void, he reasoned, then collisions and combinations must happen not just here, but everywhere. The logical conclusion was as beautiful as it was terrifying. There must be infinite worlds, some like our own, with suns and moons and living creatures, and others utterly strange, born from different swirls of the eternal atomic dance. This was not a spiritual vision, but a philosophical deduction, a cold, logical argument for a plurality of worlds that would echo down the centuries. Even in the medieval West, under the imposing shadow of a singular God and a singular creation narrative, the question would not be silenced. Scholars like Bishop Etienne Tempier in Paris in 1277 wrestled with Aristotelian dogma that declared our world unique. To challenge Aristotle was to challenge the established order, yet the bishop's condemnation explicitly stated that God's omnipotence could not be limited to creating only one world. Theologians like William of Ockham and Nicole Oresme pondered the possibility not as a statement of fact, but as a testament to divine power. Could God, in his infinite capacity, have created other worlds? And if he did, how would they relate to one another? These were dangerous, thrilling thoughts, flickering at the edges of sanctioned belief, keeping alive the flame of cosmic possibility. Fast forward through the centuries, through the dawn of the telescope and the calculus, through Newton's clockwork heavens and Einstein's curved spacetime, and we arrive at our present moment, a moment where those old myths and philosophical speculations no longer sound like the fancies of a prescientific mind. They sound, instead, like the first clumsy, intuitive grasps at a truth so vast and strange that our modern instruments and equations are only now beginning to trace its outlines. The stories of hidden realms and parallel heavens have not been discarded by science. They have been translated into the language of quantum wave functions and inflationary cosmology, of string theory landscapes and cosmological constants. The thrilling and unsettling possibility has crystallized from mist into a framework of hypotheses. We might live in just one universe among countless others. This is no longer merely a question for the philosophers or the mystics. It is a serious, contentious, and profoundly influential line of scientific inquiry. For most of human history, the cosmos was a known quantity, a stage with fixed dimensions. The Earth sat firmly at the center, a stable platform under the revolving celestial spheres, as Aristotle and Ptolemy had meticulously charted. It was a tidy, human-sized universe, comprehensible and comforting in its geocentric order. Then, in the 16th century, a Polish canon named Nicolaus Copernicus quietly dismantled that certainty. By placing the sun, not the Earth, at the center, he did more than rearrange the cosmic furniture. He initiated a revolution in perspective, a Copernican principle that would become a recurring theme in our story. We are not privileged observers. Our position is not central. Our world is not unique. This was the first great demotion. Earth became a planet, one among others, orbiting a star. The stage grew larger, but it was still a single stage. Centuries later, as telescopes improved, astronomers believed our galaxy, the Milky Way, was the entire universe, a vast island universe of stars, but still the totality of creation. This was the second great arena. Then, in the 1920s, from the summit of Mount Wilson, Edwin Hubble used the flickering light of variable stars to prove that those faint, fuzzy spiral nebula were not clouds within our galaxy, but galaxies themselves, immense cities of stars, millions of light years away. The universe exploded in size overnight. The Milky Way was demoted from the universe to one galaxy among billions, adrift in a sea of unimaginable emptiness. The pattern is unmistakable, a rhythm of revelation that seems woven into the fabric of scientific progress. Every time we believe we have found the edge, every time we construct a model that places us, if not geographically then conceptually, at the center of a finite reality, a new discovery pushes the boundary further out. Our map is perpetually incomplete, our horizon perpetually receding, and in our own time, just as cosmologists began to feel they might finally be mapping the ultimate limits of the observable universe, measuring its age, its composition, its grand structure, another idea began to take shape in the background of their equations, an idea that quietly, insistently, suggested our entire cosmos, all 93 billion light-years of it that we can see, might be only a single chamber in a palace of infinite rooms, a single note in a symphony of universes. The physicist who gave this idea its most compelling structure did not speak in the language of myth, but in the rigorous dialect of mathematics and cosmology. He spoke of multiple levels of reality, each more expansive and stranger than the last, a hierarchy of multiverses emerging not from fantasy, but from the logical extrapolation of our best physical theories. And unsettlingly, none of it was pure speculation. Each level was tethered, however tenuously, to a branch of established physics. So the question has fundamentally shifted. It is no longer, are we alone in the universe? That question has been answered by the sheer abundance of exoplanets we now know circle other stars. The new question, far more profound and disorienting, is this: are we alone in the universe, or is our universe itself merely one member of a vast, perhaps infinite ensemble? How many universes could there be? The journey to even contemplate such a question begins not in the rarefied air of mountaintop observatories or the chalk dust halls of theoretical physics departments, but in the quiet, formative spaces of a curious mind. In the unassuming town of Täby, Sweden, a young boy named Max Tegmark grew up surrounded by two distinct yet complementary worlds. His father, Harold Tegmark, was a professor of mathematics, a man of rigorous logic and analytical precision. For Harold, the universe was a puzzle to be solved, its beauty revealed not in its colors or forms, but in the elegant equations that described its behavior. He believed that everything, from the intricate symmetry of a snowflake to the majestic spiral of a galaxy, could ultimately be understood if one could only find the right mathematical relationship. The world, to him, was a grand, solvable equation. His mother, Karin, was an artist and a writer, a woman for whom the world shimmered with subjective meaning, pattern, and narrative. She filled their home with color, with poetry, with open-ended questions, and a sense of wonder at the ineffable. She saw patterns in the brushstrokes of a painting with the same intuitive grasp that Harold saw patterns in a data set. From this unique confluence of influences, Max inherited a dual inheritance, a demand for logical precision and a love for imaginative wonder. Dinner conversations in the Tegmark household were unlike those in most homes. They could swing from a discussion of abstract mathematical proofs to a philosophical debate about the nature of reality itself, from the deterministic beauty of calculus to the free-flowing ambiguity of artistic expression. Between these two poles, Max learned a crucial lesson. He learned to see equations not as dry, utilitarian formulas, but as living shapes, as works of art in their own right, describing the hidden architecture of the world. They were not merely tools, they were revelations. He was the kind of child who would stay up late sketching geometric patterns and number sequences, finding in them a beauty that others might find in landscapes or portraits. Numbers fascinated him, not because they always gave clear answers, but because they hinted at deeper hidden symmetries, whispers of a grand, coherent design running through the fabric of everything. To the young Max, mathematics did not just describe the universe, it seemed to pulse through it, a secret language waiting to be fully decoded, the native tongue of reality. And quietly, privately, he nurtured a question too daring, too grandiose to say out loud at the dinner table. What if mathematics wasn't just the language we use to describe the universe? What if, in some fundamental way, mathematics was the universe itself? What if the particles, the forces, the very space-time continuum were themselves manifestations of mathematical relationships? This thought, more a feeling than a formed hypothesis, became his internal compass, quietly steering his intellectual choices. In school, while his classmates raced through equations to get to the correct answer on an exam, Max would linger on the beauty of the process itself, on the strange fact that these abstract symbols could so perfectly model the fall of an apple or the orbit of a planet. Teachers often saw him as a dreamer, brilliant, but easily distracted by the why behind the how. He was not content with knowing that an equation worked. He was consumed with understanding why it worked with such universal perfection. When others looked at an algebraic expression, Max saw structure, an invisible architecture that seemed to shape the visible world around him. By the time he arrived at university in Stockholm, that childhood obsession had crystallized into a quiet conviction. Reality itself might be mathematical in nature. His academic papers began to draw attention, not for flashy breakthroughs, but for the way they merged hard technical logic with profound, almost philosophical questions about the nature of existence. They were papers that asked not just what is, but what does it mean to be? Eventually, that deep-seated curiosity pulled him across the Atlantic Ocean to the Massachusetts Institute of Technology, to MIT, a place where the language of the universe was spoken fluently in the scratch of chalk on blackboards and the fervent late-night debates in corridors and coffee shops. In America, Tegmark found himself immersed in a community of physicists chasing the deepest mysteries imaginable: the origin of the universe in the Big Bang, the bizarre paradoxes of quantum mechanics, the ultimate fate of the cosmos. But while many of his colleagues were engaged in the meticulous work of trying to patch together the equations of general relativity, which describes the very large, with those of quantum theory, which describes the very small, Tegmark kept circling back to his foundational childhood question. Perhaps the way forward was not to build a bridge between two descriptions of the universe, but to understand what the universe was a description of. Maybe the universe is mathematics. From that seed of an idea, nurtured over decades, grew one of the boldest and most comprehensive frameworks in modern cosmology. Tegmark did not merely propose a new twist on an old theory. He constructed an entire taxonomy of possibility, a layered structure he called the 4 levels of the multiverse. Each level emerged naturally from a different strand of well-established physics, each one more expansive and radical than the last, culminating in a vision of reality that borders on the metaphysical. But before Tegmark or anyone else could seriously argue for an infinite multi-layered reality, the universe we know had to be revealed in its staggering scale and majesty. That story of revelation, the step-by-step expansion of our cosmic horizon, is the essential prologue to the multiverse. It begins in earnest on a mountaintop in California under the clear skies of 1929. On the summit of Mount Wilson, perched high above the smog and shimmering lights of Los Angeles, the astronomer Edwin Hubble leaned into the eyepiece of the Hooker telescope. At that time, this instrument was the most powerful window on the cosmos in the world, a 100-inch giant of riveted steel and polished glass that gathered starlight with unprecedented clarity. For years, a great unresolved tension had simmered in the astronomical community concerning the nature of certain faint, cloudy smudges scattered across the night sky, nebulous patches barely discernible through smaller telescopes. Some astronomers believed they were mere clusters of newborn stars or swirling clouds of gas and dust, celestial phenomena contained entirely within the confines of our own Milky Way galaxy. Others, however, harbored a more audacious suspicion. They wondered if these spirals and ellipses were island universes in their own right, entire galaxies far beyond the Milky Way, each a separate continent of stars containing billions of suns like our own. This clash of cosmic perspectives reached its dramatic peak in 1920, in what has become enshrined in history as the Great Debate, held at the Smithsonian Institution's National Museum of Natural History in Washington, D.C. It was not merely a dry academic exchange, it was a battle over the very scale of existence. On one side stood Harlow Shapley, a forceful and ambitious astronomer from the Harvard College Observatory. Shapley had spent years meticulously mapping the distribution of globular clusters, dense spherical swarms of ancient stars that orbit the cores of galaxies like loyal satellites. By studying their apparent brightness and deducing their distances, he had made a revolutionary and correct deduction. The Milky Way was far larger than anyone had previously imagined. He estimated its diameter to be a staggering 300,000 light-years across, with our solar system positioned far from its center. This was a profound demotion for humanity, moving us from the center to the periphery. But for Shapley, this enormous scale was also a cage. If the Milky Way was so immense, he reasoned, those faint spiral nebulae must simply be small, nearby gas clouds within it. The universe, in Shapley's view, was vast but singular, a lone, self-contained island of stars. We were provincial, but we were everything. On the other side of the debate stood Heber Curtis, an astronomer from the Lick Observatory in California, known for his keen eye for photographic detail. Curtis looked at the same spiral nebulae and saw something else entirely. He had studied novae, sudden, violent stellar explosions within these spirals, and noticed they appeared consistently, dramatically dimmer than novae observed within the Milky Way. The most logical explanation was not a difference in intrinsic brightness, but a difference in distance. To Curtis, the conclusion was inescapable. These spiral nebulae were not inside our galaxy. They were far beyond its frontiers. Each one was an island universe, a separate galaxy containing its own billions of stars. The cosmos was not a single city, it was a metropolis of cities. Yet, for all the rhetorical force of the great debate, neither side could deliver conclusive proof. The technology of the time simply could not measure such astronomical distances with certainty. The question hung in a state of beautiful, tantalizing suspension. Was the Milky Way the grand total extent of creation, or merely one speck of light in an endless, dark cosmic sea? The man who would provide the definitive answer was already at work, though his path to astronomy had been unconventional. Edwin Hubble, a former Rhodes Scholar and briefly a lawyer, had found his true calling not in the courtroom but in the observatory. At the Mount Wilson Observatory, with access to the mighty Hooker telescope, he set out to solve the problem with calm, methodical determination. He knew of the great debate and wanted evidence, not rhetoric. His weapon of choice was a special class of stars, known as Cepheid variables. These are pulsating giants, stars that rhythmically swell and shrink, causing their brightness to rise and fall with a remarkably stable period. This periodicity is the key. In one of astronomy's most powerful discoveries, Henrietta Swan Leavitt, working at Harvard College Observatory in 1908, had found a direct relationship between a Cepheid's pulsation period and its intrinsic luminosity. A Cepheid that takes longer to pulse is inherently brighter. This relationship turned Cepheids into standard candles, cosmic mile markers. By measuring the period of a Cepheid's pulse, astronomers could know its true brightness. By then comparing that known brightness to how dim it appeared from Earth, its apparent brightness, they could calculate its distance with unprecedented accuracy. Hubble turned this tool toward the most famous celestial smudge, the Andromeda Nebula. Night after night, he photographed its faint light on glass plates, searching for the telltale rhythmic flicker of Cepheid variables within it. Then, one historic evening in October 1923, he found what he was looking for. On a photographic plate, he marked 3 letters next to a faint star, VAR, short for variable. That tiny penciled annotation would rewrite the cosmos. The distance he calculated from that Cepheid was unambiguous. Andromeda was not a nearby cloud. It was a galaxy nearly 2 million light-years away, far beyond the borders of the Milky Way. Curtis had been right. The scale of existence exploded in a single silent moment. What had seemed like a single grand city of stars was revealed to be but one metropolis in a vast, sprawling cosmic archipelago. The universe was filled with galaxies, each an island of billions of suns. Newspapers, sensing the profound shift, hailed it as the greatest discovery in astronomy since Copernicus. Hubble, a reserved man, became a reluctant celebrity. But for him, the true thrill was not fame. It was the vertiginous realization that the universe had no obvious boundary, no wall against which the galaxies were stacked. It simply kept going, and Hubble did not stop there. Using the same formidable telescope, he began to measure another property of these receding galaxies, their redshift. As light waves travel through an expanding universe, they are stretched, like the sound of a receding siren dropping in pitch. This stretching shifts light toward the red end of the spectrum. The greater the redshift, the faster the galaxy is moving away. To his astonishment, Hubble noticed a clear linear pattern. The farther away a galaxy was, the greater its redshift, and thus the faster it was receding. This relationship, published in 1929 and now enshrined as Hubble's law, carried a revolutionary implication. The universe was not static, as even Einstein had initially believed. It was dynamic, expanding. Space itself was stretching, carrying the galaxies apart like raisins in an ever-inflating loaf of bread. The shockwaves of this discovery reached Albert Einstein in Berlin. Years earlier, to make his equations of general relativity describe a stable, unchanging universe, Einstein had inserted a fudge factor he called the cosmological constant. When Hubble's data arrived, showing an unmistakably expanding cosmos, Einstein traveled to Mount Wilson to see for himself. Peering through the great telescope, he reportedly murmured, "I now see the necessity of a beginning." Later, he would famously call his introduction of the cosmological constant to force a static solution the greatest blunder of my career. The message of Hubble's work was unequivocal. The universe was vaster than anyone had dreamed, and it was growing larger still. Like dots painted on the surface of a balloon, every galaxy was drifting away from every other as the fabric of space-time itself inflated. There was no privileged center, no fixed edge, only endless metric expansion. With this revelation, the cosmos suddenly acquired a history. If everything is moving apart now, then rewinding the cosmic film implies a moment in the past when everything was compressed together into a state of unimaginable density and heat. That moment of explosive origin became known, somewhat mockingly, as the Big Bang. It was the hypothesized instant when space, time, matter, and energy themselves burst into being from a primordial singularity. For decades, this idea split the scientific world. Many astronomers and physicists found the notion of a definite beginning philosophically and scientifically difficult to accept. The idea that all of space and time could erupt from nothing seemed to border on theology. In opposition, a group of scientists, including Fred Hoyle, Herman Bondi, and Thomas Gold, proposed in 1948 an alternative vision, the steady-state theory. They argued that as the universe expanded, new matter was continuously and spontaneously created in the voids between galaxies, maintaining a constant average density over time. The cosmos, in their elegant view, had no beginning and would have no end. It simply was, eternal and unchanging on the largest scales, a universe with no genesis, only perpetual renewal. The Big Bang camp, however, saw in Hubble's fleeing galaxies the clear echo of a past explosion, a definitive origin. Yet, while the mathematics of general relativity and the observation of expansion strongly pointed toward a beginning, the evidence remained circumstantial. There was no direct observable relic of that first fire, no smoking gun that could prove the bang had actually occurred. For nearly 2 decades, the two camps debated fiercely in journals, at conferences, and even on radio programs. Ironically, the term Big Bang itself was coined derisively by Fred Hoyle during a BBC radio broadcast in 1949, intended to make the idea sound ridiculous. He never meant it as praise. By the early 1960s, cosmology had become a quiet battleground of ideas. The race for definitive proof was reaching a climax, and the answer would come not from a mountaintop, but from a most unexpected and humble direction. The twist of fate that followed is one of the great stories of serendipity in science. Just a few miles apart, 2 groups of researchers were unknowingly closing in on the same monumental discovery from completely different angles. At Bell Laboratories in Holmdel, New Jersey, 2 young radio engineers, Arno Penzias and Robert Wilson, were working with a massive horn-shaped microwave antenna. This sensitive instrument had been built for pioneering satellite communication experiments, but Penzias and Wilson were now using it for pure radio astronomy. Their task was seemingly mundane: to eliminate all sources of background noise from their receiver to study faint celestial radio signals. But they faced a persistent, frustrating problem. No matter what they did, a faint, uniform hiss of microwave static permeated their readings. It was a low, steady noise that came from every direction in the sky, day and night, season after season. They were meticulous troubleshooters. They checked every electrical connection, recalibrated the instrumentation, and even climbed inside the giant horn to scrub away what they jokingly referred to as white dielectric material, which was, in fact, pigeon droppings left by a pair of resident birds. Yet the hiss remained. It was not interference from New York City, nor radiation from the sun, nor any known terrestrial source. It was as if the universe itself was whispering a secret on a frequency they had accidentally tuned into. Meanwhile, just across the river at Princeton University, a team of theoretical physicists led by Robert Dicke and including a young Jim Peebles was working on a very different, explicitly cosmological project. They were actively trying to detect the faint afterglow of the Big Bang. Dicke had reasoned that if the universe began in a state of intense heat, the radiation from that primordial fireball would have cooled over billions of years of expansion, but it would still fill the cosmos. He predicted this leftover light would now be in the microwave part of the spectrum, corresponding to a temperature of just a few degrees above absolute zero. It would be a relic bath of radiation, isotropic and unchanging, a cosmic fossil. The two groups were unaware of each other's work until chance intervened. A frustrated Penzias, still searching for an explanation for his mysterious noise, called a radio astronomy colleague at MIT, who mentioned the puzzling signal to a contact at Princeton. The connection was made. When Dicke's group at Princeton heard the description of the persistent, isotropic microwave noise, the realization was immediate and profound. Dicke reportedly turned to his team and said with a mix of resignation and awe, "Well, boys, we've been scooped." What Penzias and Wilson had stumbled upon, and what Dicke's team had been searching for, was one and the same: the cosmic microwave background radiation. This was the cooled remnant of the first light that could travel freely through the universe, released about 380,000 years after the Big Bang, when the expanding, cooling cosmos transitioned from an opaque plasma of particles to a transparent gas. It was, in the most literal sense, the universe's baby picture, a snapshot of its infancy, now stretched and faded into microwave whispers, but preserved across the entire celestial sphere. The discovery, published in 1965, was the definitive evidence that clinched the Big Bang model. The steady-state theory could not account for this pervasive, cool radiation. The universe did have a beginning. Penzias and Wilson would later receive the Nobel Prize for their accidental, world-changing detection. But as with all great discoveries, solving one mystery soon revealed others, deeper and more perplexing. When scientists began to map this cosmic microwave background in finer and finer detail, starting with satellites like NASA's Cosmic Background Explorer in the late 1980s, they found a cosmos that was paradoxically too uniform. The radiation's temperature was measured at an astonishingly precise 2.725 Kelvin, but more strikingly, it was almost perfectly smooth. No matter where astronomers looked, toward dense galaxy clusters or into the deepest, emptiest voids, the temperature was the same, varying by less than 1 part in 100,000. At first glance, this smoothness seemed beautiful, a testament to a universe born in a state of near-perfect equilibrium. But on closer inspection, it became deeply puzzling, even paradoxical. The problem, known as the horizon problem, arises from the finite speed of light and the age of the universe. The observable universe today is a sphere roughly 93 billion light-years in diameter. Yet, we know only 13.8 billion years have passed since the Big Bang. This means that light, and therefore any influence that can transmit information or energy, has had only 13.8 billion years to travel. Consequently, regions of the cosmos on opposite sides of our sky are separated by a distance far greater than 13.8 billion light-years. They are, in the jargon, causally disconnected. They have never been in contact. A signal from one could never have reached the other in the entire history of the universe. How then did these vastly separated regions manage to coordinate their temperatures so precisely? It would be as if two chefs in kitchens on opposite sides of the planet, who had never communicated and used different ovens, somehow produced soufflés at the exact same temperature, to the thousandth of a degree. The standard Big Bang model provided no mechanism for this coordination. The math simply didn't allow for it. Distant parts of the universe should have evolved independently, leading to wildly different properties. Yet, the cosmic microwave background presented a sky of remarkable sameness. Physicists began to grasp the profundity of the paradox. For the universe to appear so uniform, these distant regions must have once been part of a much smaller, intimately connected volume where heat and energy could flow freely and equilibrate before being violently stretched apart. But the classical Big Bang theory offered no such early phase of connection. The universe seemed to have started off already in a state of coordinated harmony, a pre-established cosmic consensus with no obvious cause. The solution to this profound puzzle arrived in a flash of insight to a young physicist working late at the Massachusetts Institute of Technology. In 1979, Alan Guth, then a postdoctoral researcher struggling to make his mark, was pondering the mysteries of grand unified theories and magnetic monopoles. One night, he made a connection that would rewrite our understanding of the universe's first moments. He asked a breathtakingly simple yet radical question. What if, in the very first instant after the Big Bang, the universe underwent a brief, explosive period of expansion that was faster than the speed of light? In his notebook, he underlined the phrase, "spectacular realization." This spark ignited the theory of cosmic inflation. Guth proposed that a minuscule fraction of a second after the beginning, around 10^36 to 10^2 seconds, the universe was dominated by a peculiar form of energy that caused a repulsive gravitational effect. During this epoch, space itself expanded at an exponential superluminal rate. The universe did not just grow, it inflated, ballooning in size by a factor of at least 10^26 in a blink of time. This inflationary burst elegantly solved the horizon problem and other deep cosmological puzzles. The entire observable universe, all 93 billion light-years of it, was once a tiny subatomic-sized region before inflation. Within this infinitesimal volume, every part was in causal contact, allowing temperatures and energies to smooth out into perfect equilibrium. Then, inflation struck, stretching this tiny, uniform patch to a size far larger than our entire cosmic horizon, carrying its smoothed-out properties with it. The distant regions we see on opposite sides of the sky today were once neighbors, close enough to whisper to each other before being ripped apart by the inflationary surge. They share the same temperature because they were once part of the same, intimately connected whole. Furthermore, inflation explained why the universe appears geometrically flat, another puzzling observation, and it provided a natural mechanism for generating the seeds of all cosmic structure. Guth realized that the quantum fluctuations that are inherent to empty space at the tiniest scales would be blown up to macroscopic size by the inflationary expansion. These tiny, random ripples in the fabric of space-time would become the gravitational seeds around which galaxies and clusters would later coalesce. For years, this prediction remained untested. The cosmic microwave background appeared too smooth, but in 1992, data from NASA's COBE satellite finally revealed the telltale fingerprints. Minute temperature variations, anisotropies at the level of 1 part in 100,000 were etched across the sky, a perfect match for the Gaussian scale invariant pattern predicted by inflation. George Smoot, the team leader, famously remarked, "If you're religious, it's like looking at God." Later missions, the Wilkinson Microwave Anisotropy Probe in the 2000s and the Planck satellite in the 2010s, mapped these primordial ripples with exquisite precision, confirming a universe that is geometrically flat to within a fraction of a percent, and whose structure perfectly aligns with the inflationary paradigm. The implications of this confirmation were staggering. A flat universe, in the simplest models of inflation, is often an infinite universe. If space-time has no overall curvature, it can extend forever without looping back on itself. We are not living in a finite, bounded cosmos, but possibly in a patch of an endless, unbounded expanse. Max Tegmark, watching these discoveries unfold from his office at MIT, saw in this progression not just a series of isolated triumphs, but a coherent narrative leading to a startling conclusion. The story built, chapter by chapter. Hubble revealed the scale, moving us from a single galaxy to a cosmos teeming with them. Penzias and Wilson revealed the origin, confirming the hot Big Bang. Guth provided the mechanism, explaining the smoothness and flatness through inflation. And the satellites COBE, WMAP, Planck provided the empirical proof, mapping the blueprint of the universe in the faint microwave glow. Each discovery flowed logically into the next, constructing a ladder of understanding. And at the top of that ladder, if the simplest interpretation of the data is correct, sits the possibility of a truly infinite cosmos. From behind his chalkboard at MIT, Tegmark traced the mathematical and philosophical implications of this infinity. He performed a simple but mind-altering calculation. Within our observable universe, the number of possible arrangements of particles, while astronomically large, on the order of 10 to the power of a 118, is still a finite number. But if the universe is infinite in extent, then any finite number, no matter how enormous, becomes vanishingly small in the face of infinity. In an infinite space with a finite number of possible particle configurations within any given volume, repetition becomes not just possible, but statistically inevitable. Somewhere far beyond the 46 billion light-year radius of our observable horizon, there must exist regions of space where the arrangement of matter is identical to our own cosmic patch. Somewhere, there is a perfect copy of our entire observable universe, with all its galaxies, stars, planets, and people. A silent twin, separated from us by distances so vast that not even light from our Big Bang has had time to reach it. Tegmark liked to illustrate this dizzying concept with a disarmingly simple analogy. Socks. Imagine you wake up each morning and out of habit reach for a blue pair of socks from your drawer. You do this without thinking, a small, insignificant choice in the grand scheme of your day. Now, in an infinite universe, far beyond what we can see, there exists another version of you performing the exact same morning routine. But in that region, a quantum fluctuation eons ago led to a minute difference. This time, you reach for a red pair instead. Travel even farther through the infinite expanse, and you will find a version of you who never bought socks at all. And farther still, there exists a region where every atom, Every thought, every memory is arranged exactly as it is here and now. An exact copy of you is reading this exact sentence in a room identical to this one, unaware that you are both out there, cosmic doppelgangers separated by an unbridgeable gulf. This is the strange, inexorable logic of infinity. It does not merely allow for possibilities, it demands their realization, not once, but an infinite number of times. Just as rolling a pair of dice an infinite number of times guarantees that every possible sequence of rolls will occur, all snake eyes, all boxcars, every specific combination, so too does an infinite universe guarantee the repetition of every possible configuration of matter, up to and including the exact arrangement that constitutes you, your planet, your galaxy, and everything within your cosmic horizon. Every choice you have ever made, every path not taken, every star that has ever shone, every planet that has ever formed, will be replicated somewhere in that endless spatial expanse. And in that endless repetition, Tegmark glimpsed the first layer of a much grander structure. Infinity did not just create copies of our universe, it hinted at a deeper layered architecture of reality, tiers of existence stretching beyond the merely spatial. In 2003, Tegmark laid out this vision for the public in the pages of Scientific American. Somewhere out there, he wrote, there's a copy of you reading a copy of this article, differing only by the color of your socks. The line was whimsical, but its foundation was a radical truth. The centuries' march of cosmology, from galaxies to the Big Bang to inflation, had step by logical step built a ladder that led straight to the doorstep of the multiverse. Tegmark's first rung on that ladder was what he termed the Level 1 multiverse. The concept is straightforward, though its implications are profound. Imagine flipping a coin 100 times. In our observable universe, you might record a specific random sequence of heads and tails, but in an infinite universe, every possible sequence of 100 coin flips exists somewhere. There is a region where the coin came up heads every single time, and another region where it perfectly mirrored your exact, seemingly unique sequence. Now, scale this up from coin flips to the quantum fluctuations that seeded all structure in the cosmos. In the inflationary early universe, quantum jitters were stretched to cosmic proportions, determining where galaxies would form and where voids would yawn. In an infinite inflating spacetime, every possible pattern of those initial fluctuations is realized somewhere. Therefore, there must be regions where the fluctuations were almost identical to ours, leading to a universe almost exactly like ours, with an Earth almost exactly like ours, and a person almost exactly like you. The only difference might be that they are reading this sentence in French, not English. In another region, the fluctuations were slightly different. Perhaps a rogue asteroid never struck the Earth 66 million years ago, and dinosaurs still rule the planet. In yet another, the solar system never formed at all. This is the Level 1 multiverse. It does not require any new exotic physics beyond the well-established theories of an infinite inflating universe. It is the simplest, most conservative doorway into the concept of multiple universes. No leap of faith is required, only the acceptance of the logical consequence of infinity itself. But for a mind like Tegmark's, infinity was not an endpoint. It was merely a beginning. If the sheer size of space could spawn endless copies of us by simple repetition, what other, stranger multiplicities might the laws of physics allow? And why should the fundamental rules themselves, the constants of nature, the strength of forces, the very dimensionality of space-time, remain fixed across all of infinity? He could not leave that question alone. From the calm, almost classical infinity of Level 1, his mind turned towards stranger, more radical possibilities, and it is here, at this threshold that we shift from the gentle infinity of repetition to something far more transformative, a vision born not in the open, collaborative halls of Western science, but in the constrained, ideologically charged atmosphere of the Cold War East. Moscow, 1948. The city was a study in gray, its architecture heavy with the weight of ideology, its air cold with political control. Portraits of Joseph Stalin presided over classrooms and public squares, a constant reminder that curiosity, like everything else, was a commodity to be directed by the state. In the Soviet Union under Stalin, and later, science was not a free pursuit of truth. It was an instrument of the party, a servant to a materialist dialectic that demanded a specific kind of cosmos. Official doctrine, influenced by dialectical materialism, favored a universe that was eternal, stable, and perfectly knowable, a cosmic reflection of the supposed permanence of the socialist state. Ideas like the Big Bang, which implied a definite beginning, were seen as suspiciously theological, a concession to creationist thinking. The cosmos, they insisted, had no origin, it simply was. But Andrei Linde was a boy who did not quite fit inside this ideological box. He possessed a restless, innate curiosity, a mind that asked too many questions for the comfort of his teachers. He filled the margins of his notebooks not only with assigned lessons, but with his own symbols and wonderings, patterns that belonged to no sanctioned curriculum. His teachers wanted tidy, approved answers. He hungered for the unknown, for the edges of the map. Late at night, while Moscow slept under its blanket of state control, Linde sought intellectual escape. He devoured everything he could find, often in the form of smuggled papers, photocopies of Western scientific journals passed furtively from hand to hand, like contraband. These pages were more than just information. They were windows to a freer world of thought. They spoke of galaxies flying apart, of a cosmic explosion, of a faint hiss that was the echo of creation itself. Ideas his official textbooks either denied or ignored. To Linde, they were not heresy. They were glimpses of a larger, more exciting reality, proof that the universe was far grander and more mysterious than the borders drawn around him by politics. By the 1970s, Andrei Linde had navigated the system well enough to secure a position at the heart of Soviet academia, Moscow State University. The environment was a paradox, brilliant mathematical and scientific minds operating within an intellectual cage. Lecture halls were filled with chalk dust and a cautious, measured ambition. Professors spoke carefully, weighing every word against potential ideological repercussions. But in the spaces between official discourse, in whispered conversations over weak tea in cramped offices, in the corridors after seminars, a quiet rebellion of ideas stirred. Linde found himself among other restless young physicists who wanted more than the stale certainties of state-sanctioned cosmology. They traded rumors and scraps of information about discoveries from the West. They learned of Edwin Hubble's galaxies racing away from each other, the definitive proof that space itself was stretching. Then came the story of 1965. Two Bell Labs engineers in New Jersey, Arno Penzias and Robert Wilson, who had accidentally tuned into a mysterious microwave hiss that permeated the sky, the leftover heat of the Big Bang itself. The evidence was undeniable. The universe had not always been. It had a beginning, a fiery birth that no Soviet textbook would dare to mention. Then, in 1981, news of another breakthrough seeped through the Iron Curtain. Alan Guth, a young physicist at MIT, had published a seminal paper proposing cosmic inflation. The idea was intoxicating. In the first unimaginable instant after the Big Bang, roughly 10 Weitner 32 seconds, space ballooned faster than light, solving profound puzzles about the universe's smoothness and flatness. For Linde, trapped in Moscow, it was both thrilling and deeply frustrating. The equations were elegant, but when he worked through Guth's specific model, he identified a critical flaw. In Guth's original old inflation scenario, the phase transition that ended inflation happened too abruptly and unevenly. The universe would have been left riddled with topological defects, cosmic scars, and strange remnants that we simply do not observe in our smooth, structured cosmos. It was a brilliant story with a broken ending. The theory needed a more graceful, seamless conclusion, and Linde could not stop thinking about how to mend it. The flaw in Guth's model became an obsession. Night after night, in his small Moscow apartment, Linde worked by the light of a single lamp, pages of calculations scattering across his desk. He explored every conceivable variation, searching for a version of inflation that could transition smoothly to the hot Big Bang we observe. And then, a revolutionary thought began to crystallize. What if inflation did not have to end everywhere at once, in a single synchronized event? What if, instead, it ended in patches, like bubbles forming in a pot of endlessly boiling water? Some regions of space would stop inflating, cool down, and become universes like ours, while the space between them continued to inflate eternally, pushing the bubbles forever apart. By 1983, after years of intense, isolated work, Linde had his breakthrough. He called it chaotic inflation. Guth had lit the first spark, but Linde transformed it into a self-sustaining cosmic fire. Inflation, Linde realized, could be a perpetual process. It did not need a special, finely tuned starting point. Due to quantum fluctuations, some regions of a primordial field would always have the conditions to trigger exponential expansion. These regions would inflate, and within them, quantum fluctuations would create new regions that would themselves inflate. The process would be eternal, unbounded in time and space. Think of the cosmos not as a single firework, but as an infinite frothing ocean of inflationary energy, a multiverse. In this ocean, bubbles constantly nucleate where the inflationary energy decays. Each bubble is a separate universe, sealed off from its neighbors by the relentlessly inflating space that stretches between them. As a bubble forms, the inflationary energy within it converts into particles and radiation, creating a hot Big Bang inside that bubble. Every bubble universe has its own Big Bang, its own beginning, born from a local cessation of inflation in the eternal background meta-universe. And here lies the profound leap. The properties of each bubble, the laws of physics that congeal within it, do not have to be the same. As the inflationary field decays in a given bubble, it settles into one of many possible stable states, or vacua. Each vacuum state corresponds to a different set of physical constants, a different strength for gravity, a different mass for the electron, a different number of spatial dimensions that become large and stable. One bubble might have laws perfectly tuned for chemistry and life. Another might have gravity so strong that it collapses instantly into a black hole. Another might have no stable atoms at all. Some bubbles could be vast and long-lived, others could be stillborn. There isn't just one cosmos anymore, but a frothing, eternally regenerating sea of universes, a cosmic landscape of incalculable variety. No one could say how many exist. The number could be finite, but astronomically large, or truly infinite. And from our perspective, trapped inside our own bubble, we could never cross the inflating expanse to visit another, nor even see beyond our bubble's edge. Yet, according to Linde's math, the process never stops. Somewhere in the meta-universe beyond our cosmic horizon, new universes are being born at this very moment. For Linde, who finally immigrated to the United States in 1990, to take a position at Stanford University. The metaphor was deeply personal. His own life had mirrored his theory. He had escaped the sealed bubble of Soviet ideology and censorship, crossing an intellectual inflation zone to a new world of free inquiry in California. A world with different rules, brighter possibilities, buzzing with open debate. His multiverse was not just a cosmological model, it was a reflection of lived experience. But Linde's revolutionary idea of eternal inflation in bubble universes opened an even deeper question. If these bubbles truly exist, are they merely variations on a theme, governed by the same fundamental equations but with different dial settings? Or could they be fundamentally alien, operating under entirely different laws of physics, where reality itself rewrites its core script? Initially, most physicists brushed off eternal inflation and the bubble multiverse as untestable speculation, beautiful mathematics perhaps, but not serious science. Then, a surprising and powerful ally emerged from an unexpected corner of theoretical physics, one that seemed to provide the very different scripts that Linde's bubbles needed. In the 1970s, a young physicist named Leonard Susskind, who had once worked as a plumber in the Bronx, was wrestling with one of the most intractable puzzles in science, uniting quantum mechanics with general relativity. His approach, among those of others like John Schwartz and Michael Green, was radical. What if the fundamental constituents of reality were not point-like particles, but tiny vibrating loops or strings? This was the birth of string theory. Each string could vibrate in a vast number of distinct ways, like a cosmic violin string playing different notes. Each vibrational mode would correspond to a different kind of particle, an electron, a quark, a photon. Even gravity emerged naturally from a specific vibration, the graviton. To make the mathematics consistent, string theory demanded extra dimensions of space, initially 10, later 11 in M theory. These extra dimensions were imagined to be compactified, curled up into shapes so tiny that they are invisible to our everyday experience. The specific way these extra dimensions are curled determines the laws of physics that manifest in our four-dimensional world: the particle masses, the force strength, the cosmological constant. By the early 2000s, a shocking realization emerged from string theory. Instead of yielding a single, unique description of our universe, the theory of everything that physicists had hoped for, it seemed to allow for a stupendous number of possible solutions. Estimates suggested there could be around 10,500 distinct stable ways to compactify the extra dimensions. This is a number so incomprehensibly vast that it defies analogy. It is greater than the number of atoms in the observable universe by hundreds of orders of magnitude. Each solution corresponds to a different vacuum state, a different set of physical laws, a different possible universe. This collection of possibilities became known as the string theory landscape. The landscape, when combined with Linde's eternal inflation, created a compelling and daunting picture. Eternal inflation provides the mechanism to populate the landscape. As the inflating meta-universe froths, bubbles nucleate in every possible vacuum state allowed by string theory. Each bubble becomes a universe with its own unique physics, drawn from the landscape's near-infinite catalog. Some bubbles have laws compatible with stars, planets, and life. The vast, overwhelming majority do not. We find ourselves inevitably in one of the habitable bubbles, not by design, but by the anthropic principle. We could not observe a universe incapable of producing observers. This synthesis of eternal inflation and the string landscape, the level 2 multiverse in Tegmark's hierarchy, split the physics community into fervent camps. Leonard Susskind became a leading proponent, embracing the landscape as a natural and exciting outcome of the mathematics. Steven Weinberg, the Nobel laureate, saw in it a potential solution to the cosmological constant problem, the mysterious, incredibly small, but non-zero value of dark energy. In a multiverse, only rare bubbles would have a constant small enough to allow galaxies to form. We naturally reside in one of those rare congenial bubbles. Others, however, recoiled in dismay. David Gross, another Nobel laureate, dismissed the landscape idea, declaring, "This is not physics, it's giving up." For him, science's power lay in its ability to make unique, testable predictions. A theory that allowed for 10,500 possible universes, he argued, predicted nothing at all. The philosopher of science, Karl Popper's criterion of falsifiability, seemed under threat. If every possible universe exists somewhere, what observation could ever disprove the theory? Lee Smolin voiced similar concerns, warning that the multiverse could strip physics of its defining empirical rigor, turning it into a metaphysical exercise. The debate grew fierce, echoing ancient philosophical battles about the nature of reality. Is the universe uniquely discoverable, or are we, like prisoners in Plato's cave, merely seeing the shadows cast by a reality far vaster and more complex than we can comprehend? Through this intellectual maelstrom, Max Tegmark observed not as a partisan, but as a systematist, a cosmic librarian amidst a room of shouting geniuses. String theorists argued over extra dimensions and vacua. Cosmologists debated the fine points of eternal inflation. Philosophers questioned the very meaning of scientific truth. Tegmark stepped back from the fray, surveyed the swirling ideas, and conceived a project of organization. He would create a hierarchy, a layered map of reality that could accommodate all these competing visions, placing them in a logical structure that the human mind could navigate. He proposed a taxonomy of multiverses, a sequence of 4 levels, each encompassing and transcending the previous one. Level 1, as we have seen, is the simplest, our infinite, inflating universe, where beyond our horizon lie regions with the same laws but different initial conditions, leading to copies and near copies of our world. It is the multiverse of infinite space. Level 2 is the realm of Linde's eternal inflation and Susskinyud string landscape. Here, we move beyond variations in arrangement to variations in the laws themselves. Each bubble universe is a separate domain with potentially different constants, different dimensionality, different fundamental particles. The difference between level 1 and level 2 is the difference between rolling dice an infinite number of times within the same game versus playing an infinite number of completely different games, each with its own unique rulebook. To Tegmark, this was not science fiction. It was a structured, logical framework for contemplating the vastness of existence, a cosmic filing system for infinity itself. Yet, as he placed these ideas onto their conceptual shelves, Tegmark noticed a gap, a different kind of multiplicity that did not fit neatly into the categories of spatial extension or varying physical laws. It was a multiplicity born from the heart of quantum mechanics itself, a vision that suggested reality branches not across space, but across time and possibility. This puzzle had been sitting in plain sight, largely ignored since 1957 in the doctoral thesis of a young graduate student named Hugh Everett. And it was to Everett's tragically overlooked idea that Tegmark and the evolving concept of the multiverse would turn next. The autumn sunlight of the late 1950s slanted through the ivy-covered Gothic arches of Princeton University, warming stone courtyards where the next generation of physicists gathered to debate the future of their field. Chalkboards in Palmer Hall were crowded with the elegant, inscrutable notation of quantum mechanics. The air in seminar rooms hung thick with cigarette smoke and intense concentration. The Second World War was over, but a new Cold War tension simmered, fueled by the nuclear arms race and the urgent quest to master the atom. In these halls, the bizarre counterintuitive rules of quantum mechanics reigned supreme. For 3 decades, since the 1920s, Erwin Schrödinger's elegant wave equation had provided a precise, deterministic mathematical description of the wave-like behavior of particles. It was a thing of beauty if you knew the quantum state, the wave function of a system at one moment. You could in principle use Schrödinger's equation to calculate its state at any future time. The evolution was smooth, continuous, and utterly predictable. But there was a glaring, uncomfortable catch, one the students were taught as an addendum to the pristine mathematics. The wave function they learned does not just keep evolving forever. The moment you make a measurement, something drastic and inexplicable happens. The wave function collapses. All the smooth, spread-out probabilities, the superposition of states, instantaneously snap into a single definite outcome. A particle that was in a superposition of being here and there suddenly is found either here or there. This collapse postulate was not part of Schrödinger's original equation. It was a rule tacked on later, primarily by Niels Bohr and the Copenhagen School, to make the abstract math align with the concrete single-outcome reality we perceive in the laboratory. It was a necessary but deeply unsatisfying patch, a surrender to pragmatism over principle. In the quiet hallways of Princeton, this inconsistency was like a hairline crack in a flawless diamond, small, almost invisible to the untrained eye, but impossible for the sharpest theoretical minds to ignore. Hugh Everett III was a 26-year-old doctoral student working under the legendary John Archibald Wheeler. He was a man of formidable intellect and blunt questioning. He asked a question that cut to the core of the problem. If the mathematics of quantum mechanics, Schrödinger's equation, never mentions collapse, why should reality? What if we took the equation completely seriously at face value? What if the wave function describes not just particles, but everything, including measuring apparatuses, laboratory notebooks, and the physicists themselves? If you follow Schrödinger's equation rigorously, then collapse never happens. Every possible outcome contained in the superposition continues to exist. The universe, at the moment of a quantum event, doesn't choose one path. It effectively branches, with each possible outcome realizing itself in a newly created, separate, but equally real thread of reality. The famous Schrödinger's cat thought experiment is not both alive and dead in some ambiguous pre-measured state. In Everett's view, the act of opening the box causes the universe to split. In one branch, the observer finds a living cat, and the story continues from there. In another, equally real branch, the observer finds a dead cat, and that timeline unfolds independently. Both outcomes are real, both exist, but the observers in each branch are unaware of the other. To make this concrete, consider a simple quantum experiment, the double slit. In the standard interpretation, a single electron passes through 2 slits simultaneously in a superposition and interferes with itself, creating a wave-like pattern on a screen. But when a detector is placed to determine which slit it went through, the interference pattern disappears, and the electron behaves like a particle going through one slit or the other. The act of measurement collapses the wave function. Everett's interpretation is radically different. The electron does go through both slits. The detector, being a quantum system itself, becomes entangled with the electron. Schrödinger's equation then describes a superposition of 2 correlated states: electron through slit A, detector registers A, and electron through slit B, detector registers B. Both states evolve forward. The universe has split into two non-interacting branches. In one, an experimenter sees a result on the detector screen corresponding to slit A. In the other branch, a copy of that experimenter sees a result for slit B. Both experimenters are convinced their outcome was the single definite result. Everett's vision was of a universe that was not a single linear narrative, but an ever-branching tree of realities, a multiverse of parallel worlds budding off from every quantum decision. There was no collapse, only constant, endless division. Everett presented his theory in his 1957 doctoral dissertation, The Theory of the Universal Wave Function. He then traveled to Copenhagen to discuss it with Niels Bohr, the elder statesman and guardian of the orthodox Copenhagen interpretation. Bohr believed physics must provide a single definite result for an experiment, something that could be recorded, shared, and agreed upon by all observers. Everett's proposal that the universe constantly fractured into countless invisible non-communicating copies sounded to Bohr and his circle like metaphysical fantasy, not science. They politely but firmly dismissed it. Deeply discouraged by the rejection from the highest authority in quantum physics, Everett abandoned academia. He turned his formidable analytical skills to a grimly ironic new field. He joined the Pentagon's weapons think tanks, working on nuclear war planning and operations research during the height of the Cold War. There is a haunting, tragic poetry in this career shift. In his equations, worlds branched endlessly, teeming with infinite possibilities. In his day job, he calculated scenarios for the extinction of all life in a single fiery branch, the ultimate final collapse. He grew disillusioned, drank heavily, and died of a heart attack in 1982 at the age of 51. In some other branch of the quantum multiverse he envisioned, perhaps Hugh Everett lived to see his idea celebrated. In our branch, his many worlds interpretation was ignored, filed away, and nearly forgotten for 2 decades. Then, in the 1970s and 80s, physicists like Bryce DeWitt and David Deutsch began to revive it. A crucial conceptual breakthrough came with the development of the theory of decoherence by Wojciech Zurek and others. Decoherence explained why we never perceive superpositions of macroscopic objects like cats or measuring devices. It is not because the wave function collapses, but because quantum systems inevitably interact with their surrounding environment, air molecules, photons, the atomic vibrations of the apparatus itself. This interaction irreversibly leaks quantum information into the environment, effectively erasing the interference between the different branches. The branches don't vanish, they simply become separated and unable to communicate or interact with each other. Think of it like this. Imagine the pure, coherent sound of a single violin note in an anechoic chamber. That's a quantum superposition. Now place that violin in a bustling city square. The note is still played, but its sound is immediately drowned out, mixed with and rendered inseparable from the noise of traffic, conversations, and wind. The original note's identity is lost to its environment. That's decoherence. The different branches of the wave function are like different musical pieces being played simultaneously in soundproof rooms. You, as an observer, are inside one of those rooms. You hear your piece clearly and are completely unaware of the others. This gave Everett's ghost a solid physical mechanism. Experiments like the double slit, delayed choice quantum eraser, and modern quantum computing experiments began to be interpreted more naturally through the many worlds lens. In the Everettian view, the electron truly goes through both slits, but the universe, including the detecting screen and the physicist, splits into branches corresponding to each possibility. Tegmark embraced this interpretation with enthusiasm. To him, decoherence was not a mysterious add-on, It was a practical, environmental effect that explained our subjective experience of a single classical reality. It showed that the many worlds interpretation was not a philosophical fantasy, but the most straightforward reading of the uncontroversial Schrödinger equation, once you included the environment in the quantum description. So when Tegmark integrated Everett's vision into his grand hierarchy, it became the level 3 multiverse. This level is distinct. Level 1 multiplies universes across space. Level 2 multiplies universes across a landscape of physical laws. Level 3 multiplies universes across quantum possibilities within a given space-time region with given laws. Crucially, Tegmark argued that Level 3 does not add more universes on top of Levels 1 and 2 in terms of mathematical possibilities. If Level 1 is truly infinite, then for every quantum branch in our region, there is already an identical branch realized somewhere else in the infinite spatial expanse. Level 3 is in a sense a reinterpretation of the same vastness from a different perspective, from the perspective of quantum branching rather than spatial separation. But its philosophical impact is profound. It means that every choice, every chance event, every quantum dice roll that ever happened spawned new universes. Somewhere in the branching tree of quantum reality, a version of you took that job you turned down, married that person you didn't call, survived that illness that claimed you here. All those roads not taken are in the Everettian sense, roads that were taken just in other branches of the wave function. This idea of branching realities, of parallel lives shaped by different choices, proved irresistibly compelling, not just to physicists but to storytellers. It seeped from the pages of academic journals into the language of cinema, giving narrative form to our deepest existential wonderings. Films became thought experiments in Everettian logic. Consider Everything Everywhere All at Once. The protagonist, Evelyn Wang, a weary laundromat owner overwhelmed by taxes and familial discord, is suddenly thrust into contact with her infinite alternate selves across the multiverse. Every choice she ever made, or didn't make, created another version of her life. In one branch, she is a martial arts master. In another, a glamorous movie star. In another, a chef with hot dogs for fingers. The film takes the dry, branching mathematics of Everett and translates it into a chaotic, emotional, and deeply human exploration of regret, potential, and the search for meaning amidst infinite possibility. All those versions of you, all struggling, all containing fragments of a whole you can never fully know. Or reflect on Mr. Nobody, perhaps one of the most haunting cinematic explorations of the multiverse. The film opens with a simple, heartbreaking human dilemma. A young boy named Nemo. Nobody stands on a rainy train platform. His parents are separating. His mother boards the departing train. His father remains on the platform. Nemo hesitates, torn between two impossible loves. In that single agonizing moment of indecision, the film suggests reality fractures. From that point, Mr. Nobody does not follow one life. It follows all of them. We see Nemo grow into parallel adulthoods, a rich but emotionally barren businessman, a passionate but doomed lover, a solitary astronaut, an aging man in a distant future. Each timeline unfolds with impeccable internal logic from that one pivotal choice, illustrating how every decision, no matter how small, ripples out into an entirely different world. The film's genius is its refusal to designate one timeline as the real one. They are all equally real, overlapping, competing narratives in a quantum superposition of a life. By the end, Nemo himself understands that he is not a single self, but a nexus of possibilities, a living manifestation of the Everettian wave function. Hollywood is drawn to this idea because it mirrors a universal human experience, the haunting echo of the paths not taken. Everyone, at some point, wonders about the alternate version of their life, the career abandoned, the relationship not pursued, the word left unspoken. Everett's Level 3 Multiverse offers a strange cosmic comfort. It suggests those paths are not lost to imagination. They are real, playing out in full color and detail in other branches of reality, other rooms in the infinite mansion of existence. Somewhere in the quantum multiverse, you did have the courage to speak your truth. Somewhere, you did board that plane. Somewhere, the coin flip came up the other way, and everything changed. Yet, for all its narrative and philosophical power, the Level 3 multiverse, like the others, left some fundamental questions unanswered for certain thinkers. Why this particular set of quantum rules? Why this specific mathematical structure underlying reality? This drove other rebels to propose different, even more exotic visions of multiplicity. In 1992, the theoretical physicist Lee Smolin proposed a daring alternative: cosmological natural selection. Smolin suggested that universes could reproduce. He postulated that every black hole, when it collapses to a singularity, might spawn a daughter universe in a region of spacetime causally disconnected from our own. Crucially, in this birthing process, the fundamental constants of physics could undergo slight, random variations, mutations. Universes that are more prolific at producing black holes would in turn generate more daughter universes, passing on their fertile physical laws. Over cosmic time, the multiverse would evolve through a form of Darwinian selection, favoring laws that maximize black hole production. Instead of finches with different beaks on the Galapagos, we get universes with different strengths of gravity or values for the cosmological constant across a cosmological landscape. Smolin, often a critic of string theory and the anthropic reasoning associated with the Level 2 landscape, offered a testable, if highly speculative, prediction. Our universe should be nearly optimal for black hole production. His cosmic Darwinism extended the logic of branching and variation into a grand evolutionary framework. Roger Penrose, the renowned Oxford mathematician and Nobel laureate, offered a different cyclical vision. Unconvinced by inflation and skeptical of Smolin's biological analogy, Penrose proposed conformal cyclic cosmology in the 2000s. In his breathtaking model, our universe is just one aeon in an endless, infinite sequence. As our universe expands forever, driven by dark energy, all matter will eventually decay via proton decay, and black holes will evaporate via Hawking radiation. After inconceivable spans of time, the universe will contain nothing but massless particles, photons, gravitons, spread infinitely thin. Penrose showed that this ultra-smooth, empty, infinite future state can be mathematically rescaled or conformally transformed to look identical to the ultra-smooth, empty, high-energy initial state of a Big Bang. The end of one aeon becomes the beginning of the next in an infinite cycle of death and rebirth. In Penrose's view, universes do not branch or bubble outward. They succeed one another in a majestic, eternal loop, like the mythical phoenix rising from its own ashes. Tegmark's taxonomy had the flexibility to accommodate these visions as variations or extensions of his core levels. Whether universes branch, bubble, evolve, or cycle, they all share a common theme. Reality is not singular. Our cosmos is not the entirety of existence, but for Tegmark, even this comprehensive menagerie of multiverses was not the final step. All these levels, the infinite space, the inflationary bubbles, the quantum branches, the evolving or cycling cosmos, still operated within the realm of physics. They took our laws or variations thereof as the foundational given. Tegmark began to circle back to his childhood intuition, to the question that had never left him. What if physics itself is not foundational? What if the particles, the forces, the waves, and even space-time are merely surface phenomena, emergent from something deeper, more abstract, and more fundamental? What if reality is not built from physical substance at all, but from mathematical relationships? That line of questioning would propel him to propose the most radical, all-encompassing level of all, a vision that attempts to answer not just how many universes, but what is a universe. By the early 2000s, Max Tegmark had established himself as a respected cosmologist at MIT, known for his technical work on the cosmic microwave background and large-scale structure. But among colleagues, he had also earned a reputation for his fearless, almost philosophical bent of mind. Students affectionately nicknamed him Mad Max, not for recklessness, but for his willingness to venture into conceptual territory others deemed too speculative, too far from the safe shores of empirical testability. While many of his peers focused on tightening the nuts and bolts of inflationary models or analyzing the latest satellite data, Tegmark kept asking the meta question: what kind of thing is the universe, ultimately? His answer, fully articulated in his 2014 book, Our Mathematical Universe, was shocking in its simplicity and radical scope. He proposed that the universe is mathematics, not that mathematics is a useful human invention for describing the universe, but that physical existence and mathematical existence are one and the same. The Schrödinger equation, Einstein's field equations, the Lagrangian of the Standard Model, these are not just highly accurate models, they are the reality they describe. There is no separate substantive layer of stuff, particles, fields that the math is approximating. The mathematical structure is the stuff. This is the mathematical universe hypothesis, MUH. Tegmark states it plainly. Our external physical reality is a mathematical structure. That is, a set of abstract entities with relations between them, like the set of integers with the relation of addition, or the set of points in a geometric space with relations of distance and angle. Our particular universe, with its three spatial dimensions, one time dimension, and specific laws like quantum field theory and general relativity, corresponds to one particular, exceedingly complex mathematical structure. But if this is true, then a breathtaking conclusion follows. Every other self-consistent mathematical structure also exists as a physical reality. There is a universe for every possible consistent set of mathematical rules. Somewhere out there in the Platonic realm of ideas made physically real, there is a universe that is a four-dimensional hypersphere with different quantum rules. There is a universe that operates like Conway's game of life, a discrete cellular automaton. There is a universe whose logic is non-commutative, where A times B does not equal B times A. If it can be defined coherently in mathematics, it exists as a physical universe. This is Tegmark's Level 4 multiverse. It is the ultimate ensemble, transcending and encompassing all the others. Levels 1, 2, and 3 are all specific mathematical structures within the infinite library of Level 4. Our infinite inflating universe, Level 1, is one mathematical structure. The landscape of string theory bubbles, Level 2, is a more complex mathematical structure describing an eternally inflating meta-universe with multiple vacua. The branching quantum multiverse of Everett, Level 3, is the mathematical structure defined by the Schrödinger equation applied to the entire cosmos. All of them are subsets of the set of all mathematical structures. To illustrate this dizzying concept, Tegmark often turned to literature, specifically to Jorge Luis Borges' 1941 short story, The Library of Babel. Borges imagined a universe as a vast, perhaps infinite, library containing every possible book of a certain format. Most books are gibberish, random concatenations of letters and spaces, but a tiny, vanishing fraction contain coherent, beautiful stories, or true accounts of history, or prophecies of the future. The librarians wander the endless hexagons, sometimes finding meaning, often despairing in the overwhelming noise. Tegmark's Level 4 multiverse is the Library of Babel, but instead of books, the shelves contain mathematical structures. Most are incoherent. They may be simple, sterile, or internally contradictory in a way that precludes the emergence of complex, self-aware substructures like us. But a tiny fraction are rich and structured enough to allow for the evolution of complexity, consciousness, and beings who can ponder their own mathematical nature. We, of course, find ourselves in one of those rare, structured mathematical universes capable of harboring us. Tegmark's conviction was not merely a dry philosophical stance. It was rooted in an aesthetic sense, a feeling for pattern and symmetry he inherited from both his mathematician father and his artist mother. To him, the idea that mathematics is reality was the ultimate synthesis of the two worldviews. The ultimate artwork is the structure of existence itself, written in the language of mathematics. Our cosmos, for all its splendor, is but one canvas in an infinite gallery of possible realities. Tegmark was not alone in moving toward this ultra-abstract vision. Other thinkers, approaching from different angles, were converging on similar territory. In 2003, the Oxford philosopher Nick Bostrom formulated his now famous simulation argument. Bostrom reasoned that if any advanced civilization ever attains the ability to run extremely detailed, conscious simulations of reality, ancestor simulations, and if they have any interest in doing so, then the number of simulated beings would vastly outnumber the beings in the base, physical reality. Therefore, statistically, we are more likely to be simulated beings than base reality beings. Bostrom's argument does not claim mathematics is reality. It claims our reality is a computation running on some substrate, likely mathematical in its rules. If Tegmark argues the rules of chess exist eternally, Bostrom suggests we are pieces in a specific, rendered game of chess. Meanwhile, from the study of black holes, physicists like Gerard Hooft and Leonard Susskind developed the holographic principle in the 1990s, arising from the work of Jacob Bekenstein and Stephen Hawking on black hole entropy. The principle suggests that all the information contained within a volume of space can be encoded on its boundary surface, like a hologram where a three-dimensional image is stored on a two-dimensional film. Some versions of string theory concretely realize this as the AD-CFT correspondence. The implication is profound. Our seemingly three-dimensional universe might be a projection of information stored on a distant, two-dimensional surface. Once again, the fundamental stuff is not matter, but information, a close cousin to mathematics. Even earlier, pioneers like Konrad Zuse, the German computer scientist, speculated in 1969 about digital physics, suggesting the universe might be a giant cellular automaton, a computation unfolding on a discrete grid. Stephen Wolfram later championed similar ideas, showing how simple computational rules can generate astonishing complexity, suggesting our universe's laws might be the simple program of a deeper computation. When you stand back and view these visions together, Tegmark's mathematical universe, Bostrom's simulation argument, Suskind's holographic principle, Zuse's digital physics, a common profound theme emerges. They all point toward a dematerialization of reality. The universe is not primarily made of solid stuff. It is made of relationships, of information, of bits, of mathematical structure. Matter and energy are secondary phenomena emergent from a more fundamental, abstract substrate. Physics, in this ultimate view, becomes a branch of mathematics, and existence becomes the set of all things that are mathematically possible. For some, this is the pinnacle of intelligibility, the final answer to Eugene Wigner's famous 1960 essay on the unreasonable effectiveness of mathematics in the natural sciences. Wigner marveled that mathematics, a product of human thought, should so perfectly mirror the physical world. Tegmark's MUH provides an answer. It is not unreasonable at all. The physical world is mathematics. The effectiveness is perfect because they are identical. For critics, this is a bridge too far, a descent into untestable metaphysics that abandons the empirical core of science. Yet, even the critics must acknowledge a persistent trend. The deeper physics probes, the more mathematical reality appears. From the parabolic arc of a cannonball described by calculus, to the electromagnetic waves described by Maxwell's equations, to the curvature of spacetime in general relativity, to the complex Hilbert spaces of quantum mechanics, every fundamental advance has revealed a universe written in increasingly sophisticated mathematics. Tegmark's level 4 is the logical endpoint of that trend, the final Copernican revolution. Not only are we not at the center of space, or the center of our galaxy, or the center of our universe, but our entire universe is not at the center of existence. It is one entry in an infinite timeless catalog of mathematical forms. So, we arrive at the edge of current thought, peering into the abyss of ultimate possibility. We have journeyed from the myths of countless worlds to the philosophical speculations of the Greeks, from the explosive expansion of Hubble's galaxies to the whisper of the cosmic microwave background, from the inflationary burst that smoothed the cosmos to the eternal inflation that spawns bubble universes, from the quantum branching of Everett's many worlds to the mathematical plenitude of Tegmark's final level. The question has evolved from, are there other worlds, to how many universes are there? And the answer, in its most expansive form, seems to be all that can be is. Every consistent mathematical structure, every possible set of physical laws, every variation on every theme, every story that can be coherently told, exists in the full, absolute sense of existence. This is not necessarily a comforting thought. It can evoke a sense of cosmic insignificance, of being a mere speck in a speck in a speck in an infinite regression of realities. But it can also evoke a sense of profound connection and awe. It suggests that the human mind, through mathematics, is not just a passive observer of an alien reality, but is somehow tuning in to the very framework of that reality. We are not just reading the universe's book, we are, in our act of comprehension, engaging directly with its substance. As we end this contemplation, the night sky outside is quiet. The stars we see are but the nearest sparks in our own local cosmic bubble, a single room in an unimaginably vast mansion. The myths of old were not wrong, they were intuitive. The hidden realms, the parallel heavens, the countless worlds, they are all out there in some form or another, in some level of the multiverse. The universe is not just stranger than we imagine. As J.B.S. Haldane once said, it is stranger than we can imagine. But through the twin tools of rigorous science and fearless imagination, we are learning to imagine it anyway, to trace the contours of a reality whose vastness humbles and inspires in equal measure. And so, as we turn from these cosmic vistas back to the familiar confines of our world. Let the immensity outside serve not as a cause for despair, but as a reminder of the incredible adventure of being here, now conscious and curious, in this particular universe, on this particular planet, able to ask the question, and brave enough to follow the answer wherever it may lead, even into the heart of infinity itself. Good night.